Okay, the next one, there they ask us, is this set comprising of the three 2 by 2 matrices? Is it a basis for M22? Now, M22 is a set of all 2 by 2 matrices where the entries are real numbers. So is it a basis? So we need to answer two things. We need to first establish whether the set is linearly independent, and number two is we need to establish whether the set S spans the whole vector space M22. Right, so let's take my set S to be the set of three matrices, and now the question is this a basis for M22? So we need to verify two things again: the linear independence and the span property. So now I have a suspicion that this set is not a it's not a basis for M22. Right. So I'm going to claim that S is not. S is not a basis, right? So claim S is not. Okay, it's not a base. All right, so how would I do this? We can do it by contradiction. Let's suppose it is a base. Let's suppose it is a base. Suppose S is a base. Suppose to the contrary. So suppose to the contrary. Suppose to the contrary. That S is. All right, so suppose to the contrary that S is a basis for M22. So therefore we've got that S has to be, it has to be a linearly independent set, and S has to span M22. All right, so therefore thus S, the span of S, that has to happen under assumption. The span of S has to be the whole M22. Okay, so what is the implication of this? What is the implication of this? From this, I'm going to continue there. So from this, it follows that this matrix is in the span of S. Okay? Where this matrix is clearly an element of M22. Now because these two sets are the same, it means that every 2 by 2 matrix is in the span of S, and every matrix in the span of S is also in M22. Okay, so therefore 1, 1, 1, 1 will be in the span of S because S spans M22. Okay, so there we've got our statement. So what do we know? What do we know about the fact that this matrix is in the span of S? What does that tell us? It tells us that 1, 1, 1, 1 is a linear combination of the vectors in S. So therefore, there exists So there exists scalars K1, K2, and K3 such that, right, so there exist those scalars such that you can express 1, 1, 1, 1 as a linear combination all right, there we go. We take our first element. Okay, that's the first one. All right, we take our second vector there and place it so that we can form the equation. There we go. All right, the third one, there we go. Okay. All right, there's the scalar, the first scalar, K3. All right, there's the second scalar, K2. All right, and there's the third scalar, K1. Okay, and so clearly we know because by assumption, every vector in M22 is a scalar multiple, is a linear combination of the vectors in S. Alright, so there we've got our first equation from that part there. Okay, there we've got our second equation from that part there. Okay, and our third equation follows from that part. There we go. Okay, and our last equation, we can get from basically from that part, that part, that part, and that part there. All right. And what is that equation actually? It's 1. It's 1 on the left, and on the right you've got 0k1 plus 0k2 plus 0k3. Right, so that is going to be 0. And we're going to have equality there. So 1 is definitely has to be 0, and this is a contradiction. Alright, so clearly this is impossible. Alright, this is impossible. So this is impossible. This is impossible. Alright, so whence we get a contradiction. And so whence we can say that S is not, it's not a basis, as we said that M22 and the span of S, we've just proven that M22 is not contained in the span of S, because there's a point in M22 that is not in the span of S, and we've just shown that this point here is not in the span of S because it's not a linear combination of the vectors in S. Alright, so Theorem 1 states that if S is a set of vectors that's a basis for a vector space V, then every vector V in V can be expressed in the form V equals a linear combination of the vectors in S in exactly one way. Now remember I said that for the basis we had the two properties. For something to be a basis for a vector space V, you need the vector space V to be spanned by the basis. In other words, every vector in the vector space must be a linear combination of the vectors in S. Also, you need the vectors to be linearly independent. Right. Now, the linear independence, this is where the importance of the linear independence comes in. Because the linear independence property of a basis ensures that you can only express a vector V in uniquely one way as a linear combination between the vectors and the basis. So there's no way that you can have multiple representations for a vector. So each vector V has a unique representation. So that is useful. It falls a bit outside of the scope of this course, but it becomes very useful later on. So let's see why this is the case. Alright, so let's take V and write it as a linear combination of the vectors in the basis. Right. Now let's say there's another representation for V in terms of the vectors of S. Alright, so let's take the vector V, the vector V1, the vector V2, up until the vector Vn, with scalars d1, d2, dn, Alright, so there you've got two different representations. Now you can subtract the one equation from the other equation, and basically you're going to get that C1 minus D1 V1 and C2 minus D2 up until Cn minus Dn Vn is equal to the zero vector. Okay, now this is the formula for linear independence, right? So the only solution for this, the only solution for these scalars, is going to be where C1, okay, C1 equals D1, C2 equals D2, because all of them have to be zero, the trivial solution, okay? And the reason for this is V1 up until Vn, they are linearly independent vectors. Linearly independent. Alright, so that is the usefulness of the linear independent property of the basis. Because now the basis, each vector representation is unique. Each vector representation is unique. Okay, so now, so these coefficients, right? They're all the same. I cannot represent the vector v in two different ways. They're always going to be the same, and it follows from the fact that the vectors are linearly independent. All right, so if S is a basis for a vector space V, right? Now, if we know we can write V as a linear combination of the vectors in S, that representation of V in terms of the basis, if we go and read off these values C1 up until Cn, those are called the coordinates of V relative to S. And by the previous theorem, because we only have one unique representation, this coordinate, the coordinates of V relative to my basis S, those are going to, it's going to be unique for each vector, because the linear combination representation of each vector is unique by the linear independence property of a basis. So these vector coordinates in Rn given by that is called the coordinate vector of V relative to S. Okay, so it's basically, so if you go back here, you go and read, you represent V as a linear combination, and then you go and read these values off, and you place them in a, coordinate vector, and that is that's a coordinate vector of V relative to S. Now, alternatively, you can also write it as a column vector, but okay, that it depends also depends on the textbook. Some textbooks generally go for the column vector representation. But it doesn't matter as long as you know what, as long as you can interpret what they mean with it. Okay, so this brings us to the following example. So there, they find coordinate vectors relative to the given basis for each of the following. Okay, I just want to look at another example. We're going to go back a little bit in this section, and just quickly look at a previous example we did. All right, so from a previous example we did. We have the set S, and we have P2, and we showed that S spans P2. And we also showed that S is linearly independent. So we showed that S is a basis. Okay, S is a basis. It's a basis for a P2. Okay, now to illustrate this coordinate vector relative to S, so what we're going to do is, we already did the calculations. Alright, so there take a polynomial from P2, and then we look at the linear combination. Okay, there we have our linear combination. Now what is the coordinate vector of the vector A1, A0 plus A1x plus A2x squared? What is the coordinate vector relative to S? What is that coordinate vector? Right, so we solved for K1 as that quantity. Okay, so okay, so we solved that. So with that, we're going to place that firstly there. That is our first value. We solved for K2 as this quantity here. So there, that is our second coordinate. All right, and then we solved for K3 as that quantity there, so that is our third component of our vector. Okay, so that forms our coordinate vector. All right, so that is the coordinate vector of the vector, well, it's a coordinate vector relative to the basis S of this particular vector here. Okay. So that is what I'm looking for. It's these quantities that I solved in my linear combination representation. So that's an example of finding the appropriate vector, the coordinate vector relative to the basis S. Okay, so we are asked to find the coordinate vectors relative to the given basis for each of the following. So the first one there is look at V in R3, and we are asked to find the coordinate vectors with respect to the standard basis. Okay, so there you've got your vector in R3, and what's the standard basis again? It's the standard unit vectors. Right, so there's my three standard vectors. So we just need to go and express, because it's a basis, right, so we need to go and just express the vector V as a linear combination of the vectors in S. So take these scalars which I want to solve, be scalars. Alright, such that so we can express V as a linear combination of these vectors in the basis. Okay, now you can by inspection actually solve this pretty easily. You can quickly see that what the answer is here. Right, so it's not terribly complicated. Right, so we know what vector V is. Right, so we take our vector V. Okay, and you can basically solve for, you can easily solve for K1. You can solve for K1 as 1, and you can solve K2 as 2, and you can solve K3 as, right, so the K3 as 3. So what is the coordinate vector now? So the coordinate vector of V with respect to the basis S is going to be the vector, it's going to be the vector 1, 2, 3. Okay. Right, the next one we are asked to find the coordinate vector V relative to the basis S. Now the basis you're given is different in this case. Right, so there we've got the vector V again, and we've got a different base S in this case. So what we want is, we want to solve that scalar equation. Alright, so let K1, K2, K3 be scalars such that right, so there you've got your vector. Right, there you've got your first vector in your basis. Second vector. Right, third vector. Right, there's my first scalar. Second scalar. Right, third scalar. So from that equation, it then follows that you get three equations. Okay, so you get 1 is equal to K1 plus K2 plus K3. That's the first equation. Right, second equation we get. Right, and our third equation, we also get a value for K3. Okay, therefore we can solve from 2, we can solve for K2 as minus 1. And from equation 1, we can plug in both those quantities and solve for K1 as minus 1. Alright, so the coordinate vector then becomes, for V, the coordinate vector with respect to the basis S is simply the vector given as minus 1, minus 1, and 3. Okay. Alright, next we look at number 3, find the vector, the vector's coordinate vectors relative to the given basis, and the basis in this case is the standard basis. Alright, so we've got the vector in P2, 1 plus 2x squared, and we've got the standard basis for P2, which is 1x squared. Alright, so we need to find the coordinate vector with respect to the basis S. Okay, so let K1, K2, and K3 be scalars such that right, so there we've got our vector. Right, so there's our first vector, second vector, third vector. Right, so there we get K3. There's K2. Alright, there's K1. Right, so that's the equation you need to solve. So gathering all the terms, and again, don't forget, this has to be true for all values of x. These two functions need to be the same on the left-hand side and the right-hand side for all values of x. Okay, so gathering all the terms, you find those the polynomial on the left-hand side equals to 0 for all values of x. And again, if this quantity is not 0, then you have a polynomial on the left-hand side of degree 2, and on the right-hand side you have the 0 vector, and this has to be true for all values of x. And the problem with this is, again, is for any value of x that you plug in there, you're gonna get a root. So that pretty much means that all x's are going to be roots to this polynomial, which is impossible. You can have at most 2 roots for a polynomial of degree 2. So that thing has to be 0, right? So we immediately, the implication of this is, again, K3 has to be 2 minus K3 has to be 0. So therefore K3 is 2, okay? And again, here, if this thing is not 0, it's going to mean you get a polynomial on the left-hand side that's degree 1, and degree 1 polynomial can have at most 1 root. And because this is true for all values of x, it means that you have a polynomial of degree 1 essentially that's got infinitely many roots. That's impossible. So the only other alternative is for K2 to be 0. That's the only way this can be satisfied. And then the last one, again, that must also be, again, that has to be 0, because if it's not, then you've got a non-zero polynomial on the left-hand side equals to a 0 polynomial on the right-hand side. So therefore you need K1 to be 1. It's the only other option. Okay, so it's easy to see that basically the yeah, I mean, well, you could have done this actually by inspection. So the vector P coordinate vector with respect to the standard basis S is pretty much the vector 1, 0, 2. Alright. Okay, we have the last one. There they ask us find the coordinate vector of that polynomial relative to a new basis. And it's the basis 1 plus x, x minus x squared 2. Okay, there we've got your vector p, and you've got your basis s. Okay, so let k1, k2, k3 be scalars such that okay, first vector my basis, second vector my basis, okay, third vector my basis, right, so there we've got our first scalar, right, second scalar, right, third scalar. Okay, so there's my equation, and from there we can quickly set up the necessary information. So there we've got our equation that we can set up, and again by the same argument we have, because for all x's this has to be 0, that has to be 0, and that has to be 0. Okay. Alright, so we can solve for k2 as minus 2. Right, so we can also we can solve k1 as minus k2 and plug the value for k2 in there and get k1 being equal to 2. And lastly, we can solve for k3 as a half 1 minus k1, and plugging k1 in there we get a half a minus 1, and so k3 can be solved as minus a half. Okay, so from there what does our coordinate vector become? The coordinate vector of the polynomial p with respect to this basis is the coordinate 2, minus 2, and minus a half. Okay. Alright, so that is coordinate vectors with respect to different bases. Now, unfortunately, it falls a bit outside of the scope of this course, but the usefulness of this comes more later in chapter 4, where it's a concept known as changing of basis, and for that we need the coordinate vectors, but that's going to fall outside of the scope of the course.